With our ever-increasing knowledge of enzyme kinetics, we're now equipped to understand a graph of the initial velocity as a function of substrate concentration. The function that results when this is graphed is a rectangular hyperbola in which that hyperbola asymptotically approaches a value called Vmax. Now, it turns out that, like every good function, this function is no exception and has an equation that describes the function. That equation is an incredibly famous equation called the Michaela Menten equation. Now, don't hold your breath. Pretty soon, we're going to derive that equation, so we will have the full understanding of it. But the first thing that I want to do is to look qualitatively at the graph and the way in which we already understand much of what is shown by this graph.
Is that we're looking at initial velocity as a function of substrate concentration. So this is different than the graph that we were looking at before, where we were looking at the change in product concentration as a function of time. Now we're looking at the substrate concentration and the initial velocity as a function of that substrate concentration. Okay, so what we see then is that this is a rectangular hyperbola, and we see that it is approaching asymptotically the Vmax value, or the maximal velocity. Now what we notice and what we recognized already is that at high substrate concentrations, the concentration of substrate stops mattering. Now, let me show you that by actually drawing on the graph. So if we're at very low substrate concentrations, right, and you change the substrate concentration from here to here, okay, not very good lines, but they'll work. So we have a change in substrate concentration like that. Notice how much that affects initial velocity. So at low substrate concentrations, initial velocity changes greatly with a change in substrate concentration. However, as we get to higher substrate concentrations, aka saturation, and we change by about the same amount in terms of substrate concentration. Now notice what happens here. Change from here to here. Wow, check that out. Okay, pretty hard to make a line here, but we'll get it done. From there to, wow, I'm not even sure that I can see enough of a difference to point out to you. Okay, so without a better ruler and more quantitative techniques, it almost looks like there's no effect of this change, right? It looks like they come out very similar. So what we see then is at high substrate concentration, initial velocity becomes independent of those substrate concentrations. This is saturation. So now we remember that this is true, right? Remember when we looked at the equation and assumed that at high substrate concentrations, the velocity became dependent upon enzyme concentration only, right? So at high substrate concentrations, we saw that there was very little change and that enzyme concentration was really what mattered. So at low substrate concentration, the reaction rate is sensitive to small changes in substrate. We saw that happening. At high substrate concentrations, the enzyme becomes saturated with substrate, and we know that at that point we can assume that all enzyme is bound to substrate, and we can write that equation that we wrote earlier, that initial velocity now is a function only of total enzyme. So we see this now, what we looked at with equation before, we see this now graphically by actually looking at the rectangular hyperbola and how it comes to a flat or asymptotic point at the top of the curve as substrate concentrations increase. So as enzyme becomes saturated with substrate. So also at saturation, notice something else is happening. Now our graph doesn't go far enough to really see this in good light, but if we continued going on, what we would see is that with time the function is approaching Vmax. So it basically is headed, in that direction, and as we headed off it would asymptotically approach Vmax. So at very, very high concentrations, one could make the assumption that initial velocity equals maximal velocity. So we could plug that in, approximately equal to Vmax. You could plug that into this equation and actually write another equation that Vmax at saturation, Vmax is equal to K2 times E total. Excellent. So this is all going to come into play now. We're starting to really hit the take-home messages with this graph being one of the first. This graph really showing us how substrate concentration affects velocity. The higher it is, the less effect it has on velocity. The higher it is, the more we can just express velocity as a function of enzyme concentration. Awesome. One more thing before I leave this behind then is the fact that we have a sort of special substrate concentration, and we have a name for it, that occurs at half maximal velocity. So the concentration of substrate at half maximal velocity is something that is termed the Km, or the Michaela Menten constant, and we'll talk a bit more about where it comes into play from an equation derivation standpoint. But from this standpoint, what we can see is that Km is equal to the substrate concentration when the initial velocity is at 1/2 Vmax, or half maximal. Excellent. Km's going to come back, and we're starting to get towards these take-home messages. Bear with me. I know this is hard to wrap your brain around. Let's go ahead and derive the equation now. Please don't memorize this derivation, but learn from it and think about what is applying from our earlier ideas. Okay, so here's our equation. We recognize it from before. K1, the rate constant describing this forward reaction. K-1 describing this backwards reaction. K2 describing, of course, the rate limiting or catalytic step. Now, it was a little bit past the time of Maud Michaelis or Maud Menten and Leonore Michaelis that another researcher, George E. Briggs, and actually there were two of them working together, George E. Briggs and J.B.S. Haldane, I believe is the pronunciation. And these guys came up with what is termed now the steady state derivation of the Michaela Menten equation. And that's what we're going to be looking at here, is the steady state derivation. And it is based on this idea that the reaction is in a steady state. And by that, what we mean is that enzyme substrate complex is degraded at the same rate that it is formed. Now this is going to occur, it occurs actually coinciding with the initial velocity, which is convenient, and is forming as rapidly as it is decomposed. Now we're not assuming saturation at this point, and we'll see that that's very important to deriving the equation. We can assume saturation later and look at how it affects the function, and how we can see it affecting the function with respect to the equation. So let's look at then this derivation. We can write down what this means then, writing the rate equations for both the formation and the decomposition of the enzyme substrate complex, and knowing that they're in an equality to one another. So enzyme substrate complex is made by what process? Just this one, right? Just this reaction. It's made by just that reaction. Now it's decomposed in two reactions, right? So it's decomposed in this reaction and in this one, right? So we can set those then as an equality. Let's begin by looking at the decomposition, the two ways in which that occurs. So writing the rate equations for each one, right? We take the rate constant, K minus 1, times substrate, ES, right, times concentration of the substrate, which is the enzyme substrate complex, plus, okay, so it's decomposed in another way, K2 times substrate, which again is enzyme substrate complex. But this decomposition, so this is decomposition, equals formation. So they're formed as rapidly as it's decomposed. So let's look at the one reaction by which it's formed, is this one here. K1 is a pertinent rate constant times concentration of enzyme, right? Again, concentration of substrates, which are these. Excellent. So now we have an equation that it describes steady state, if you will, where rate of formation equals rate of decomposition. Now there is some plugging in that we can do in this equation to help us further our derivation. And there's also an equation that we should always keep in mind for initial velocity. What is the rate equation describing initial velocity? We've written this several times, right? Initial velocity equals K2, the rate constant for the rate limiting step, times yes. So bearing in mind that this is true in terms of discussing the initial velocity. Now we're going to go on and the first step that we're actually going to take in our derivation is noting that we could plug in another expression for the E here, for E free, because that is E free. Okay, so that E free we know is going to be equal to E total minus enzyme substrate complex. Oops, get that right. Nice. So the reason for maybe going ahead and wanting to plug in this right here expression into this spot is so that we can start to get like terms. So we're eventually going to be solving for enzyme substrate, and so this will enable us to eventually get there.
Your notes contain a nice skeleton outline for deriving the Michaela Menten equation, and you're welcome to use that. But I highly suggest just getting out a huge piece of white paper, maybe the back of an old poster you thought you would never use, and actually just being super minds-on as you derive this equation. I love that term, minds-on, thinking about what you're doing. And I'm going to try to do that with you. But in fact, if you want to pause the vodcast right now and actually try deriving it first on your own and then coming back and joining me, that would be the best way to go about this. So remember when we had left off, we had just expressed the rate of formation being equal to the rate of decomposition of the enzyme substrate complex. So remember we had talked about the K minus 1 times enzyme substrate concentration plus the K2 times enzyme substrate concentration as being equal to K1 times, and we had just done a little bit of plugging in because remember in order to express the E free, we had just decided to replace that with a term that had enzyme substrate in it. So enzyme total minus enzyme substrate would be another expression for enzyme free. And then, of course, that whole thing was times the concentration of substrate. So this puts us in a place where we can group the rate constants, because as it turns out, that's how we're going to get the Michaela Menten constant, Km. So let's group these K minus ones, K2, just pulling those out and dividing through by K1, and then getting this compilation of a rate constant times enzyme substrate is going to be equal to the expression E total minus enzyme substrate times substrate. And not a lot has changed there except for that we grouped the rate constants. But what's cool about that is that, as it turns out, this right here is an expression for Km. So we can replace that entire compilation with Km. And that's what we'll do now in our next step, is simply to call that Km times enzyme substrate equals, again, everything the same over here, enzyme total minus enzyme substrate, get the bracket there, times concentration of substrate. Okay, so at this point we now have an expression that is looking as though we could think about distributing the substrate concentration here and then being able to isolate enzyme substrate terms. So let's just use distributive property over here to take enzyme total times substrate minus enzyme substrate. My hand is going to get tired. Derivations will do that to you. Times substrate. And then, of course, over here still Km times enzyme substrate. But this puts us in a better place to group the terms with enzyme substrate in them. So if we want to go ahead and bring that over where we have Km times enzyme substrate plus enzyme substrate times substrate is equal to E total times substrate. Okay, so we're looking pretty good there, so that we could group enzyme substrate, right? So we could actually pull that out. Concentration of enzyme substrate. And then that leaves us with Km plus the concentration of substrate equals E total. Being able to simplify a bit here, times substrate concentration. And now we could actually solve for enzyme substrate, which is cool. Remember, that was one of our objectives. And so enzyme total times, I forget sometimes how much fun it is to derive equations. It just feels good. Km plus concentration of substrate. Okay, good. Hey, now wait a minute. We're starting to recognize something, because remember that we thought back to this equation, and I'm going to make this a different color. Remember that we had said at saturation conditions that initial velocity was equal to K2 times enzyme substrate because all of the enzyme was bound to substrate. So if we notice that, we actually could take this enzyme substrate concentration and literally plug, so we know that this enzyme substrate concentration is equal to this entire compilation of terms over on this side of the equation. So if we take this whole thing and we plug it in here, then we're getting a new and fun equation, okay? So initial velocity is equal to K2 times this entire jazz right here, right? Enzyme total times substrate over Km plus substrate. And that's starting to look pretty great. And if we just go ahead and write this, I think you're going to recognize we don't really need to have that in a quantity there, so because it's just a multiplication. So you'll be beginning to recognize something, I hope, that I just write. So K2 times enzyme total times substrate over Km plus the concentration of substrate. If you look at this, and my writing is a little messy right there, but recognize that we actually have seen this at saturation conditions. We know that that is the expression for initial velocity, and that specifically when we are at high substrate concentrations, recall that this is how we expressed Vmax. So when that function is approaching maximal velocity, essentially we could plug in right there. Remember that what we had written, Vmax equal to K2 times enzyme total. So this actually can be replaced by Vmax. So check it. We have now got this sweet equation. Initial velocity is equal to Vmax times substrate concentration over Km plus substrate concentration. And guess what? We did it. That is totes the Michaela Menten equation.
And a sexy equation that describes then the curve that the rectangular hyperbolic curve that we just looked at. So this is the equation that describes that function, that curve. So initial velocity equals Vmax times substrate concentration over Km plus substrate concentration. This is the Michaela Menten equation. So put the star in your notes next to this equation. No, I will not ask you to derive the equation on the exam. I do like some of the logic that goes into its derivation. So, kind of understanding why we plugged in for what is kind of interesting. But more than anything, it's what we're going to talk about now that I want you guys to have a grasp of what that is, what this means to us. So what the Michaela Menten equation means and how it describes the function that we graphed. So let's look at both of those things. And I think the best way to do that is to think about changes that occur on the graph that graphs initial velocity as a function of substrate concentration. So let's start out by looking at that. So it describes the shape of the hyperbola, the rectangular hyperbola. Let's look at a situation then where we're at very high substrate concentration, so very far to the right on that graph. And now I just have to draw that graph on here because we're just going to be at a loss if we don't have it, right? So this describes this. Initial velocity, function of substrate concentration, rectangular hyperbola, I'll make it red. Of course, it's approaching Vmax. which I didn't do a very good job of at the very end there, did I? Just make that a little bit better. That's better. Approaching Vmax, great. And then we know that at half maximal velocity, right about there, right? That concentration of substrate is called Km. Cool. So this equation describes this function, and let's look at that come to life. So at very high substrate concentrations, the concentration of substrate is much, much greater than Km. So we can just go ahead and look at that in terms of this equation. If the concentration of substrate is much, much greater than Km, then what we see is that Km becomes negligible. So we have an equation then that is Vmax times substrate concentration divided by Km plus substrate concentration this approaches zero, right? Or I shouldn't say it that way. This is negligible as compared to the substrate concentration, right? So Km is much, much less than substrate concentration. So we get then this equation that is Vmax times substrate divided by substrate. And check this action. God, I love canceling stuff. Okay, and initial velocity, you guessed it, equals maximal velocity at saturation, right? Where substrate concentration is very, 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 very high. So we see it approaching Vmax. So initial velocity, oh, look at that, that's sweet. Okay, so at very, very low substrate concentrations, right? Then substrate much, much less than Km. Okay, so this time when we plug in initial velocity equals Vmax times substrate concentration. This time we say then that the substrate concentration is negligible with respect to the Km because it's much, much larger. Okay, this is at very low substrate concentrations, way down here, right? Okay, so at these very, very low substrate concentrations, we see that initial velocity becomes a linear function of, that's a K, of substrate concentration. Y equals mx plus b, right? So it becomes a linear function described by a slope of Vmax over Km. So this is the slope. So at very low, very, very low concentrations, basically you've assumed a linear function with a slope of Vmax over Km. So at low substrate concentrations, the velocity then is a linear function of the substrate concentration, or depends linearly upon that substrate concentration. So we could go ahead and write that in. Linearly proportional I'm having some spelling issues. Linearly proportional to concentration of substrate. Excellent. So, let's try one more. Let's just try one where we're actually looking at the point at which substrate concentration equals Km. So we'd actually plug in Km for substrate concentration. Let's see what that does. Ooh, this is fun. So if we plug in that initial velocity equals Vmax times Km divided by Km plus Km, we get initial velocity equals Vmax times Km divided by 2 Km. Oh, spec that. Km's cancel. And look at this. Look at this. Initial velocity is Vmax over 2. Yeah, yes it is. Vmax over 2, right? We already defined that, and now we see the equation tells us to. So we can derive that idea that Km is a substrate concentration at half maximal velocity. That is just some excellent stuff.